In this video, we want to find the first order partial derivatives of the given functions. The first function is f equals ln of square root of x to the 2 plus y to the 2 plus z to the 2. Before we start, let me remind you the derivative of ln. Derivative of ln of an expression is 1 over that expression times by derivative of that expression because of the chain rule. So we can consider all of this as the expression, and so we can use this formula right away. But it's better to simplify the given function if it is possible. Then finding the partial derivatives would be easier. So do not start right away. First, let's try to simplify this. This function f can be written as 1/2 ln of x to the 2 plus y to the 2 plus z to the 2. Why we can write this function in this form? Radical means power 1/2. And we know that one of the properties of logarithmic function ln, or logarithmic function in general, is that we can bring the power from here to the front. So first we use this property of ln functions, logarithmic functions, and then we are going to find the partial derivative. This function has 3 variables, so for this function we have partial derivative with respect to x, with respect to y, and with respect to z. Partial derivative of f with respect to x. For finding partial derivative with respect to x, 1/2 is the coefficient. Derivative of ln based on the formula is 1 over the expression times by derivative of the inside. What is the derivative of the bracket? What is the derivative of x to the 2 plus y to the 2 plus z to the 2 with respect to x? Only to x. Because the variable is x, the others are constant. Derivative of y to the 2 and z to the 2 with respect to x is 0, so times by 2x. The 2 from numerator with that 2 in the denominator cancels, so the answer is only x goes in the top, and the bottom is x2 plus y2 plus z2. In a similar way, you can see that the partial derivative with respect to y is y over x2 plus y2 plus z2. And because of symmetry, also you can claim that the partial derivative with respect to z is z over x2 plus y2 plus z2. So sometimes it's better to first stop, check if you can simplify the function simplified, then take partial derivatives. Look at this function. The function f is given log x in the base y, and we want to find the partial derivative of this function with respect, of course, to x and with respect to y. Let me remind you the formula that we know for logarithmic function. If you remember, when we have a log x in the base b, its derivative is simply 1 over x, 1 over whatever this expression is. In this case it is x. It can be other expression, any expression, 1 over that expression times by ln of the base, ln of b. This is the formula. And of course, if this expression is other than x, we have to multiply it at the end by derivative of that expression. But this is x, so this is the formula. For finding derivative of this function with respect to x, partial derivative with respect to x, we can use right away this formula, and the answer would be 1 over x ln of y. But the problem is that if we want to find the partial derivative with respect to y, then this is a number, this is a constant, and the variable is here. And then this formula doesn't work for that. What we have to do in this case? Here, you need to know a little about logarithmic function. You need to know the properties of logarithmic function. We can write log x in the base y in the form of ln of x over ln of y. And now we have an expression that is equal to this. So instead of taking derivative of this, we can take derivative of this, because we know how to take derivative of this. But for this, we don't have any formula. And of course, for finding the partial derivative of f with respect to x, also you can take derivative of this with respect to x. And of course, the answer would be the same. But for partial derivative with respect to x, we don't need to do this conversion. But for partial derivative with respect to y, because the variable is in the base of the logarithm, which is very unusual, we have to do this conversion. We rewrite log x in the base y as ln of x over ln of y, and then we take derivative. For taking derivative with respect to y, attention, variable is y, and so x is the constant. We use quotient rule. Based on the quotient rule, derivative is derivative of the top, which is 0, times bottom, 0, minus, we leave numerator, times by derivative of the denominator. Derivative of ln of y is 1 over y. Remember, derivative of ln of x is 1 over x. Derivative of ln of y is 1 over y, all over the denominator to the 2. This is quotient rule. So the answer can be written as negative ln of x over y all over ln of y to the 2, which can be written as negative ln of x over y ln of y to the 2. We divide this by this, and this is the answer. Another method that you can use for finding the partial derivative of this with respect to y is to use this identity. Log x in the base y is equal to 1 over log 1 over log y base x, and then use quotient rule to find the derivative of this. And because y now is in the front of log, is not in the base of x, in the base of log, so you are fine to use the formula that we know for logarithmic function. But maybe you are finding this method easier. Now look at this function. Function f is given integral from y to ln of x e to the t secant t dt. The function f has two variables, variable x and variable y. Attention, t is not a variable. This is something that is a little confusing sometimes. Because you see t here, you think, okay, f is also a function of t. No, t is not a variable here. When we take integral from this expression, at the end, we are going to plug in ln of x and y for t. So, our function would be only in terms of x and y, not t. Because we replace, in the definite integral, we know that we are going to replace the variable with the upper bound and lower bound. So, f has only two variables, and those are x and y. So, for this function, we want to find the partial derivative with respect to x and partial derivative with respect to y. For finding these partial derivatives, you need to remember fundamental theorem of calculus. What was fundamental theorem of calculus? Let me remind you. Based on the fundamental theorem of calculus, we know that if we have an integral from a constant, a number, to x of f of t dt, its derivative is simply f of x. So, what is fundamental theorem of calculus? In simple word, when we have integral, if we take derivative from that, when we have a definite integral from a number, a constant, to x, the variable is here. If we take derivative from that, the integral notation, the integral operation cancels completely, because derivative and integral are opposite. And that variable that is in the top, in the upper bound, x, would substitute for t. So we plug in x for t, and the answer is just f of x. So let's do this process for this question. Here, first we want to find the partial derivative of f with respect to x. And as you can see, x is only here in the upper bound. So this is a constant. This is like a. And it has nothing to do with the taking derivative with respect to x. So we plug in that ln of x for every t that we have in our function. Attention, this is our function, not dt. This is not part of the function. This is our function. We replace every t with that. So the answer would be e to the power of ln of x secant of ln of x. But attention, in the fundamental theorem of calculus, upper bound is only x. But here we have something other than x, it's ln of x. So you have to apply chain rule here also. Based on the chain rule, we have to multiply this answer by derivative of the upper bound, derivative of the ln of x. So we have to multiply this answer that we got so far by derivative of ln of x. But what is derivative of ln of x? It's 1 over x. So this is the answer. We plug in this for every t, and we multiply by derivative of this expression, this upper bound. This is your final answer. But in this case, you can do a little simplification in your answer, but this is optional. We wanted to find the partial derivative with respect to x, and this is our answer. But let me remind you something. We know that e to the power of ln of x, because exponential function and logarithm function ln are inverse of each other, so e to the ln of x is equal to x. Based on this, e to the ln of x is x. So this expression is x. This x with 1 over x cancels, so the answer of this question at the end is just secant of ln of x. Now let's move to the other partial derivative with respect to y. For finding the partial derivative with respect to y, the problem that we have is that the y is not in the upper bound. So we cannot use the fundamental theorem of calculus right away. Here we use a property of integral. We say this integral can be written as negative integral from ln of x to y e to the t secant t dt. We switch these two and we put a negative outside. This is one of the properties of integral, definite integrals. Now y is in the upper bound, so we can apply the fundamental theorem of calculus. We want to find derivative of this function, which is an integral. Based on the fundamental theorem of calculus, simply plug in that upper bound for every t. And don't forget you have a negative outside. So the answer is negative e to the y secant y. And because it's just y, it's not a function, it's just y, derivative of y is 1, so you don't need to multiply by derivative of the upper bound. Basically you are going to multiply by derivative of upper bound, but it's y and derivative of y is 1. So this is the answer for partial derivative with respect to y. I hope by watching this video you have learned more about finding partial derivative for a little complicated functions. If you like this video, please subscribe in my channel and see you in the next videos.